Okay, so in this lecture, we will study the transformation of input output forces, and then we will complete that remaining little amount of discussion on velocity kinematics. And we have been waiting for this lecture to complete this topic of static forces to complete first, because the transformation of velocities and static forces have a very interesting similarity, and the issue of singularity uh, manifests itself in a unified manner on both velocities and static forces. Okay, so first we handle the business of static forces. So basically this is static force. That means no inertia issues will be considered here. I was just going to make the mistake of not sharing screen. Yeah, so now I'm sharing the screen with you. So when we study the issue of static forces, then our focus is on input output transformation. Basically, we try to map the end effector forces to the joints, active joints. And in that, dynamic forces are out because we are talking about static forces. And even gravity we do not consider in this discussion, because if we want to take the gravitational forces and map them similarly, then from the point of application of that particular gravitational force, we can go in a similar manner. And in this study, therefore, separately, we do not need to bother about the weights. So whatever we are doing for the end effector forces, which it encounters from the environment, that same thing we can do for every weight. Now, you see, when we studied velocity kinematics, then we started from the frame and went till the end effector. The reason of starting from the frame was that the motion of the frame was known. In the case of force analysis, we do the other way around, because the force at the end effector is known. At the base, we don't know the force and moment interaction between the frame and link 1. A lot of joint reactions are involved. At the end, however, we know if the robot is doing nothing, it's just there. If the hand is free, then this force from the environment on the hand is 0. If it is carrying a tool, a weight, then force from the environment is the weight of that load. Okay. Now, if the robot is doing some assembly operation in which it is perhaps tightening a bolt or handling a wrench or trying to cut something, okay, against a force, then whatever is the force moment combination that it gets from the environment, which it has to counter, that is the force and moment on the end effector from the environment. And that is what we will try to map to the joints. And that force and moment combination which it encounters from the environment, that you can get by a wrist sensor, by a force torque sensor mounted on the hand. That is, just before the contact of the hand with the environment, you mount this, through which the force and moment of the environment actually goes to the manipulator. Okay, so from link to link. So we take Fi as the force exerted on link I by link I minus 1. Okay. So the link N will be giving to the environment. That is the force we are denoting with Fi. Okay. Similarly, Ni is the moment exerted on link I by link I minus 1. And at the end, it will be link N by link N to the environment. Okay. So equilibrium demands that since link I will give a force Fi plus 1, okay, to the next link and get a force from the previous link I minus 1, which will be minus Fi minus 1. Okay. So this is Fi, which link I is, okay, this is actually, yeah, for the equilibrium of link I. That is, it is giving a force I plus 1 to the environment. So from the environment, it is getting a force minus Fi plus 1, and Fi is a force which link I minus 1 is giving link I. And this superscript I here simply means that both the forces are expressed in the frame of reference of I. You can express the vectors in any frame of reference using its xyz components. In particular, you can do that in frame I. One important point is that all the vectors among which you do any vector operations, all of them have to be expressed in the same basis. Otherwise, these operations will not make sense. So IFI minus IFI plus 1 equal to 0. And this will imply that these two are equal. Okay. That is, whatever force link I got from the previous one, it is passing on to the next one because it cannot keep it. Okay. For equilibrium, this is needed because we are considering no other force. And since we are studying the input output transformation, so in between any dynamic forces, any inertia forces of link I, any weight of link I, we are not considering. Okay. Those things separately we can consider if we want. Now, when we talk about moments, so link I minus 1 is applying this moment on link I, and link I plus 1 is applying this moment minus Ni plus 1. Okay. And since it is applying a force also, Fi plus 1, at a point other than the origin of the frame I, therefore, that position vector cross that force also is there. Okay. So since this force is minus Fi plus 1, so the moment of the force is this position vector cross minus Fi plus 1. And this is equal to 0. And that means I, Ni, the superscript is common, so it doesn't matter. It is the frame of reference. So Ni is this. Okay. So from these two equations, if you know the force interaction, force and moment interaction between link I and I plus 1, then you know the right side. Okay. Right hand side of these two you know. And in that case, you can determine the left hand side, which is the force and moment interaction between link I minus 1 and I. So like that, starting from the end effector, the force and moment that it gives to the environment, you can know if you know that it is free or you know the weight that it is carrying, or you have got the reading from the force torque sensor that you have mounted there. And from there, you get the force moment interaction in the previous link, then the previous link, then the previous link, and so on, till all the force moments at the joints you can find out. Okay. And now each of these, that is Fi-Ni combinations at every joint, actually has three components. Three components here, three components here, so total 6 components. So 3 independent components of forces, 3 independent components of moments, total 6 force moment combinations, force moment components. Now, in the frame of reference I, since you are anyway expressing it, so in that, if the joint is revolute, then all these 3 force components, XYZ, all 3 force components will be joint reactions, because it is because of the design that because of the force it is not running away. So the force is actually from the joint. So that is a joint reaction. Okay. If the joint is revolute, and in that case, even from the moment, out of the 3 components, the X and Y components will be joint reactions. It is a Z component where the architecture of the joint is not offering any resistance, not offering any force. It is the motor mounted there which is. So for the moment vector, if you take the Z component, either you write as the dot product or you write as this. It is the same thing. Okay. That will be the joint torque. Okay. If the force is prismatic, if the joint is prismatic, then all the 3 moment components will be joint reactions. It will be the Z component of the force interaction at the joint, that will be the input force, that is this, if the joint is prismatic. Here we are still calling it tau I, because tau is taken as a generic term for forces and torques on the input side. The way for joint variables in such vector equations, we used theta and separately said that if a joint is prismatic, it will be the d rather than theta, and use theta vector as the general expression for the coordinates of the joints. Okay. So this we can find out. That means whatever is the end effector force moment combination, for that, by considering link by link and taking the appropriate components like this, we can find out all the joint forces and torques, whatever effort is needed to sustain that output force. Okay. This is one way to get the joint forces and torques. There is another way. Since we are transforming static forces, so we are considering the entire manipulator at equilibrium. So you can say that the virtual work by actuators through virtual displacements delta theta will equal the virtual work by the output force F equal to Fn and moment equal to Mn through virtual displacements. Okay. So virtual displacement of the hand, that is that satisfying the constraints, whatever little, I mean some infinitesimal displacements you give at the joints, which produce a similar infinitesimal displacement at the hand, then whatever are the forces, they do some work through these virtual displacements at the joints, and that entire work is available at the end effector side, okay, as virtual work. So this virtual work and that virtual work is 0. Basically, the original, you can say that all the virtual works on a system together will be 0. Okay. So if there is an input virtual work and then an output virtual work on that side, which is not done on the manipulator, but on, not done by on the manipulator, but done by the manipulator on the environment. So the corresponding work done on the manipulator by the environment will be the negative of it. So you subtract that and 0. So you can say the same thing as that the work input, the virtual work input that the manipulator is getting and the virtual work output that it is giving to the environment, they are same. So virtual work input, if a joint torque tau 1 is turning the joint through this virtual displacement delta theta 1 and so on, everybody, then together the total virtual input virtual work will be this, which together you can write vector tau transpose vector delta theta. Okay. At the end, if you see, then it will be the output force dot the virtual displacement of the hand plus the output moment dot the virtual displacement virtual rotation of the hand. Now this rotation is taken as a vector because it is a small rotation. Okay. So see, the way this you wrote as tau transpose delta theta, like that you could write this as F transpose dt and this as M transpose delta, and then you can combine them F transpose M transpose in a big row and dt and delta in a big column, and that is what you would get if you write it like this. So when you take the transpose of this is actually 3 components, fx, fy, fz. This is 3 component, mx, my, mz. Okay. So in the transpose it will be all in a row and then it will multiply appropriately with these. And now you see that this little virtual displacement, linear displacement and angular displacement, what is that? That is basically j times delta theta, which we have seen from the kinematics, and from this point onwards you start seeing the statics velocity kinematics linkage. Okay. So this dt delta is j times delta theta for every delta theta. Okay. And now you see this delta w is this and this delta w, which is equal, is this. Okay. So this and this are equal, and if it is equal for only some delta theta, then it means nothing, no big deal. But if these two have to be equal for every delta theta vector, that will mean that this tau transpose and this Fm transpose J have to be equal. Tau transpose and Fm transpose J have to be equal. Okay. And now take transpose on both sides and you get tau equal to J transpose Fm. Okay. And now compare it with this. Velocity or small motion is transformed from input side to the output side by the Jacobian transformation, and forces and moments are transformed from output side to the input side by the transpose of the same Jacobian transformation. Okay. And this gives rise to an interesting similarity, rather duality, between the velocity kinematics and statics. So whatever happens from input to output side for velocities, the same thing will happen from the output to input side for forces. Okay. So with this background, we go ahead to study two more interesting issues. One is singularity and the other is workspaces. Okay. So this we have just now seen: input output velocity force transformations are like this. For a manipulator, okay, this is a 2-hour example we are taking first. We are taking. So this point onwards, we will continue after a little break. Of course, for you, the break will be just half a minute or 1 minute. For me, it will be longer because I am stopping to record and I will continue recording after I finish my. Okay. So with this 2 degree of freedom planar robot, we will be in a position to study the idea of singularity easily. So the end effector coordinates, that is task space coordinates, will be x and y, that is position of this point. It is only 2 degree of freedom, so we are not talking about controlling theta also. Only two things, only two output coordinates you can control with a 2 degree of freedom manipulator. Theta vector has two quantities, two components, theta1 and theta2. Okay. So the end effector forces will be Rx and Ry, no talk of moment because we are not controlling it in the angular coordinate. And joint forces, there will be two torques because two revolute pairs, revolute joints. And here the derivative of this, that is the velocity of this point, is given by j times theta dot, which is the derivative of this vector. And tau, the joint torques, tau1 and tau2, are given by j transpose, this force that the hand is applying on the environment. And note that this is the input velocity which is transformed through j to the output velocity, and here it is output forces here which is transformed to the input forces, torques in this case, through j transpose. Okay, so that is the sense of the duality between velocity kinematics and statics. So at a regular configuration, if you want some motion here, some x dot y dot, then you can find out theta1 dot, theta2 dot to get it by solving this. And from some are some forces that that the environment applies on the hand, and the hand has to counter by equal and opposite. So you can find out suitable tau1 and tau2. Okay, and they are typically non-zero. I mean, it may happen that the force is so that only one of them can sustain it and the other happens to be other force input, other torque input happens to be zero. That's a different thing. But in a configuration which we call a singular configuration, where both the links are aligned like this, okay, and here you will notice that any motion that you give to the first joint, that is any theta1 dot that you give here, will produce a motion of the hand which will be in this direction, in the direction Vp, velocity possible. Okay. And if you do not give input here, you give input to only the second joint, any theta2 dot that you give, that also will produce an end effector velocity in this direction, which is the velocity possible direction. Okay. Now what happens if a velocity is required in this direction, which has a component Vp, which is possible either through a motion here or through a motion here or through some combination. Okay, but it also has a component along this direction which is not possible. Okay, so this is what happens at the singular configuration. No motion in some direction, forward or even backward, is possible. So regarding forward, you will immediately perhaps say that, well, the entire arm is completely stretched, so beyond that how can it go? Okay, but try a motion in this direction, inward. Inward is at least within the reach, right? I mean, by a folded structure of the elbow you could have reached here, but now you could have reached by a folded structure, but right now that you are not in a folded structure, you are an extended structure of the arm. Even if you want to come back inward, right at this moment, right at this configuration, there is no input velocity combination which will give you this inward motion. You cannot get it because any motion here gives a motion in this direction only. Any motion here also gives a motion in this direction only. So there is no possible motion in this direction as well as the outward direction. The reason is that when you try to put that velocity here and you try to solve this system of equations, this Jacobian transformation turns out to be singular, and Vp falls in the range of J, and that is why a singular configuration, singular matrix, and the known vector on the other side of the equations is in the range of it. So in that case, there are infinite solutions. Okay. So a calculation of the inverse velocity kinematics in the neighborhood will demand very large values of theta 1 dot and theta 2 dot. So if you demand a velocity which is somehow in this direction, has no component in the impossible direction, then theta 1 dot alone can achieve it, or theta 2 dot alone can achieve it. Okay, or some combination. There are infinite possible combinations which together can achieve this. There are infinite solutions of this system if x dot is in the range of J. And if x dot is not in the range of J, that is, if the required x dot, required V, has any component that is in this direction, then that velocity cannot be achieved. Okay, and even if the point is really not here, but a little close by somewhere, where the arm is almost extended, say this angle is rather than 180, this angle rather than 0, it is 1 degree, 2 degree, 2.5 degrees, like that, then the matrix that you get as the Jacobian transformation is not really singular. Nominally it is non-singular, but so close to singularity that when you try to invert it, it will have huge numbers in the inverse. And that is why any motion in the direction of Vp can be achieved by theta 1 dot alone or theta 2 dot alone, but not in the direction of Vi. Okay. So in this neighborhood, somewhere else also, points in the neighborhood or points in the theta 1 theta 2 neighborhood will give you, in the inverse velocity kinematics, enormous demanded velocities at the joints, which is impossible. Okay. On the other side, if you look at the forces, you will find that some forces in this direction will be supported freely, I mean without any joint torque, because you see, a torque at this joint will produce a force in this direction. A torque at this joint also will produce a force in this direction only. No torque here or here, no joint torque, okay, will produce a force in this direction. And that means in this direction, if a force is applied from the environment, it will be sustained without any joint effort. Okay. So at singularity of this kind, which is the prevalent kind in the case of serial manipulators, at singular points, at some directions, the manipulator become very rigid, and that we know that you have noticed, because against an adversary who is trying to break into your door, if you have to sustain the door with your arms only, what you do? You stretch your arms and put the elbow straight, so that you get a 0-degree angle here, and you put your entire arm at a singular configuration, so that at the joints you do not have to give effort, muscle effort. So the adversary's push is taken completely by your joints. So, I mean, if he pushes too hard, then your joint can break, but that is not what you are budgeting for. You are budgeting for your actuator failing, okay, because joints can take enormous amount of forces. And rigid body, your elbow, your arm is almost part made of two rigid links, okay. So you are budgeting against your actuators, the muscles at the joints. So in order to lessen or reduce the load on the actuators, you put your arm straight and stop the adversary in this manner. Okay. So at similar configurations, at some directions, some degrees of freedom are lost. Some velocities, some motions are not possible, and in that direction, the force carrying capacity gets amplified enormously. And the two are related. Because if motion is not possible by input torques as well as output forces, which is the same thing because it is logged, if motion is not possible, then why motion is not possible? Who is stopping it? Okay. So it is the joint reaction which is stopping it. Okay. And joint reactions up to the capacity of the joint will take forces. So whatever effort is there to push it in that direction, it will be stopped. So very large forces in the VI direction, that is RS, would be supported with 0 or very small actuator torques. Okay. In the neighborhood of this configuration, very large external forces in a specific direction can be countered with modest joint torques. Okay. Because of the same large numbers in the inverse of J, and therefore inverse of J transpose. Okay. Now we have already noticed that such situation occurs at the end of the reach of the manipulator. And you have seen that in a completely stretched condition, there is one such situation. There will be another such situation at the completely folded situation also here. Okay. So if you fold the second link completely so that the end effector point is here, then there also you will have a singularity where theta 2 is not 0, but theta 2 is pi. And in this case, that's also workspace boundary in a way. That is the boundary of the inward side, because the workspace of this manipulator will be the another region with radius, outer radius equal to L1 plus L2 and inner radius which is L1 minus L2. You see that it is very difficult to reach this place. Okay. I mean, this location, it is very difficult to reach with your hand. Okay. So, because it is too close. Okay. Now, so the whole boundary, so internal boundary of the workspace and outer boundary of the workspace. So now through this we come across workspace. Now here also you will find that towards the origin coming is impossible that you can directly appreciate, because it is not in the workspace of the robot. But from here, even going the other way will be impossible. The way from this point, from this configuration, even coming inward was impossible at this configuration. Okay. Now we come to the issue of workspace. What is workspace of the robot? So set of position orientation combinations or set of poses that a manipulator can reach or operate at. That is known as the workspace. And then there are some fine distinctions that has been made by people in the literature, and those fine distinctions had to be made because the true and complete description of the workspace is actually possible only in the full task space, which is the space of x, y, z and alpha, beta, gamma. If you can operate in a six-dimensional space of x, y, z and alpha, beta, gamma, and that is not Cartesian space anymore because the angles make it troublesome. Okay. But if you could operate in that space, okay, that is the task space, then you could simply work out a volume in that space and then say that this is the workspace in the 6D space. Okay. But that we don't work. So we try to see specific projections of this six-dimensional space in 3D space, particularly 3D Cartesian space. And while doing these projections, in literature, you will find that people have made this kind of workspace, that kind of workspace, and so on. Okay. So some classifications and terms involved have tried to segment the notion for better comprehension and visualization in 3D spaces or 2D for planar purposes. So one way of classifying workspace segments of different quality has been reachable workspace and dexterous workspace. So reachable workspace is the set of all those points where the end effector can reach, okay, with at least some orientation. Okay. Dexterous workspace, on the other hand, is the set of those points where it can reach with arbitrary orientation. That means where it can not only reach, but after reaching, it can go on dancing around at that point. Okay. So that is dexterous. And dexterity is, the literal meaning is skill, and dexterity of a manipulator is how easily it can operate in different orientations. Okay. In another classification, people talk about primary workspace and secondary workspace. Primary workspace is basically dexterous workspace in which it can do everything. Okay. So this is same as dexterous workspace. You can say that primary workspace or dexterous workspace, rather primary workspace, is that region in the task space where all degrees of freedom of the manipulator can be operated continuously. Now, this definition, primary workspace as the region where all degrees of freedom can be operated continuously, this frees the concept or the definition from this business of arbitrary orientation. Why that is an advantage? Because the manipulator may not have all 6 degrees of freedom from the beginning. Okay, it may be a 4 degrees of freedom manipulator. Then how can you say with arbitrary orientation? Arbitrary orientation is not possible. Okay, so for that robot, that region where it can utilize all its degrees of freedom continuously, all its degrees of freedom. Okay, that is, I mean, those task space coordinates which it is supposed to control. So that is, you call it primary workspace. Okay, and outside this primary workspace, there will be some additional region, additional, you know, part of the task space where all the degrees of freedom cannot be operated continuously, but some degrees of freedom can be achieved. Okay, and that is basically the reachable workspace. That is, okay, not reachable workspace minus this thing, because this has been already included in primary. So secondary is what will complete the reachable workspace. Outside that will be the regions, the vast universe of the task space, which is outside the workspace of the manipulator. So this is a sense. Now, to make a roundup of all these things, from position kinematics, velocity kinematics, statics, singularity, workspace, everything together, a schematic for the workspace of a manipulator is typically like this. In the task space, there will be a vast region where the manipulator cannot reach because its base is fixed. Okay, and then there will be a boundary inside which it can reach, and this boundary, every point at this on this boundary is an extreme reach point for the manipulator. Okay, so for example, if I keep my arm folded like this, then wherever my fingertips are, there I should be able to reach in several ways. But if I extend my arm completely, then I would be reaching a location where I cannot reach in any other manner, right? So at all the points on the boundary, that is at all the extreme reach points, there is a single configuration of the inverse position kinematic. Okay, and that can happen in two ways. One, because of a singularity that is possible, that is there when some angles have some specific values, so that the Jacobian is singular. That is one possibility. The other possibility is that in a joint there is a joint limit. For example, there may be a revolute joint which can only take positions from minus 60 degree to plus 135 degree. Okay, then at these two angles, beyond that the joint cannot go, so the end effector also will have similar limitations. Prismatic joints will always have joint limits. Prismatic joints, you cannot go from uh, Venus to Pluto, so they will always have joint limits. So boundaries appear at singularities and joint limits, and not only the outer boundary. At outer boundary, at the extreme reach point, you have only one configuration of the inverse position kinematics. You come just inside, okay, in these locations, there you will typically get two solutions of the inverse position kinematics. Okay, basically, at this point, what really happens is that as you slowly change it like this, at an extreme point, these two solutions merge together, and beyond that, those two solutions become complex. Okay, the way you take a quadratic equation ax square plus bx plus c equal to 0, and slowly change one of its parameters, say c. As you slowly change c, then you will find that the two solutions of the quadratic equation will slowly come close, 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 and then at some critical point of critical value of c, where the discriminant will be 0, the two solutions will merge. So you will have real and repeated solutions. And in that direction, if you continue to change c, then at the next value they will become complex. Okay. So this thing, those people have very well uh, experienced who have done root locus analysis of control theory. I think you will do it in the next year. Okay. So as you come inward, you might encounter another boundary through singularities and all, inside which there may be 4 solutions. Depending upon the complexity of the manipulator, even inside there may be 6 solutions. And then inside, further inside, there may be again 4 solutions. And further inside, there may be 2 solutions. Further inside, there may be no solution, which is the workspace hole. So this is a strict boundary of the reachable workspace. The way this is another strict boundary of the reachable workspace. In principle, there could be other holes also. Okay. So here the inverse position kinematic solutions inside will be 0, and outside it is anyway 0. Okay. So that is the typical schematic of a task space, and the embedding of the workspace, primary, secondary, everything in that. Okay. So with this, this entire topic of robot kinematics is over for us, and in the next lecture we will take up trajectory planning.